So 1 minus omega square term will contribute to the frequencies below and above the resonant frequency, because at resonant frequency this term is going to be 0. But you have also one more term, this omega RC the whole square, which will contribute to the bandwidth even at all frequencies. So we are going to define a factor called M, which is going to be the ratio of time constant. So first time constant RC divided by L by R. So you can write it as, it is going to be equal to R square C by L. The same expression, whatever z of s you have computed, replace that, write everything in terms of m, and you get this term. Write everything in terms of m. So your expression will be having omega tau 1 m. And if you solve this equation, you will get two frequencies, omega 1 and omega 2. Omega 1 is the old 3 dB frequency, and omega 2 is the new 3 dB frequency. 3 dB means after adding this inductor, whether this omega 2 is increasing or decreasing. Because shunt peaking is increasing the value of bandwidth. Bandwidth means I'm increasing what is FH. Here we are writing FH in terms of omega H, okay? And they found that after adding this inductor, the bandwidth is increasing to 1.85 times the actual bandwidth. So without inductor, find out the bandwidth. With inductor, you find out the bandwidth. They found the ratio is going to be 1.85 times. It is going to be large. And they say that the frequency response is peaking by 20%, which is very, very considered very, very high. So I need to have a very moderate peaking and a broad bandwidth. So that is going to be found mathematically by maximizing M. The one choice is to set the impedance of magnitude of impedance equal to R at a particular frequency. So when you do this condition, they say that the M value becomes approximately equal to 2. When M is equal to 2, the bandwidth increase is going to be 1.8 times. Okay. So substantially, they say that the peaking is reduced to 3%. So peaking it should be very, very less, because when the peaking is very high, the current flowing to the device may damage the device. So peaking should be reasonably less. Then the graph should be broad. So that is the constraint for shunt peaking. And then different combination they have studied. There are many cases where one desired the frequency response to be completely free of peaking. Sometimes peaking illam irukano. So for that, sometimes they may have minimal peaking. Sometimes they may expect the frequency response to be flat. So there are so many constraints are there. So for if you apply those constraints, they found the value of M to be 2.41. And for this value of M 2.41, the bandwidth is more by 1.72 times. So at least for a shunt peaked amplifier, both a maximally flat response and substantial bandwidth can be obtained simultaneously. So peaking is also minimal, bandwidth is also maximum. So that is what is required, because if you increase the peaking, the current flow is going to be larger and it is going to damage your device. So I have to satisfy two conditions. One is the peaking should be minimal and bandwidth should be maximum. So that is achieved by putting M value as 2.41, while the bandwidth increases 1.72.